Welcome, this is Physics 270, worksheet number 7, version A, problem 12. We have a laser light with a wavelength of 580 nanometers, and it's used in a double slit interference experiment with the slit separation of 0.25 millimeters and a scree distance of 1.2 meters. The experiment is first performed in the air. Later, the same apparatus is immersed in benzene, which has an index of refraction of 1.5, and the experiment is repeated. We want to determine the distance between adjacent interference maximums in air and the same thing in benzene. So let's see if we can get ourselves a little setup here. We'll put in the axis first, and we will put in slits here. Do it like so. Yeah, I kind of get the idea. It's not perfect, but we got our double slit spacing, and those are our slits, and this distance is 0.25 millimeters, and the screen is down here, and this distance here is 1.2 meters. We're going to call that L because that's what they called it there. And on the screen we have a series of bright spots. Our central, this is going to be the m is equal to 0. This is going to be the m is equal to 1. This is going to be the m is equal to 2. Is equal to 3. We're going to go down here with an m is equal to minus 1, m is equal to minus 2, etc. And what we're trying to determine, what they've asked us, is the distance between the adjacent interference maximums. These are the interference maximums, and we want to come up with the distance between the adjacent ones. This is the distance that we're looking for. I'm going to call that delta x. Okay. So let us assume right now that we're going to do this with air, which of course has an index of refraction of 1. And we go to our equation that says d, this is d is the 0.25 millimeters, d sine theta is equal to m lambda. And now what we want to do is use the small angle approximation, which says that the sine of theta is approximately equal to the tangent of theta, which is approximately equal to our to y over L. And so what we're talking about here, and this is kind of strange, but like if we go to the first one here, we're going to call this distance here y. I'm going to call that y1. I'm going to call that theta1. And of course this I'm calling L. And you can see from that picture that the tangent of theta1 is indeed equal to y1 over L. And what we're saying is that this is a small angle. So we're going to say that this is approximately equal to the sine of theta1. Anyway, that's the idea of the small angle approximation. So in this case, we are going to replace sine theta, we're going to replace with y over L, and then the result of that is that dy over L is equal to m lambda. And if I solve for y, I find out that y is equal to m lambda L over d. And I see a whole series of these things. M is equal to 0, plus or minus 1, plus or minus 2, dot, dot, dot. There's a whole series of these. Of course, y0 is, of course, 0. y1 is equal to lambda L over D. y2 is equal to 2 lambda L over D, etc., etc. And if we take a look at the distance between y1 and y2, y2 minus y1, that's what I call delta x in the above diagram. And that is going to be 2 lambda L over D minus lambda L over D, which is, of course, lambda L over D. And this is the story here, is that the double slit interference produces equally spaced maximums. And that spacing is what I call delta x, is a lambda L over D. Okay, so in air, our spacing, our delta x, let's call it delta x air, is equal to our 580 nanometers for the wavelength times the 1.2 meters for the spacing divided by the 0.25 times 10 to the minus 3 meters for the slit width. And when I calculate that, I'm going to get something in meters, and I'm going to calculate that. And the answer that I got here is 0.002784 meters, or we could write that as 2.784 millimeters in air. All right, now what we want to do it in benzene, and in the benzene, the wavelength changes. The wavelength is reduced. So lambda in the benzene is going to be lambda in the air divided by the index of refraction of benzene, 580 nanometers divided by 1.5. And that gives us a wavelength of 386.67 nanometers. And then if we want to calculate the interference max, delta x benzene is going to be lambda benzene times L divided by D. L and D don't change just because you put it in benzene. Only the wavelength changes. 2 divided by 0.25 times 10 to the minus 3, and I will calculate that. And I get 0.001856. And that's in meters, or we'll write it as 1.856 millimeters. There we go. Our slits, our interference spacing in air and in benzene. Okay.